I just want to, most of the organization for the workshop was done by Mignon. So we should thank him for it.
Well, thank you. That's entirely untrue, but I don't mind.
And now the last mathematical word in the workshop will be given by Mignon.
Thank you very much for staying until so late. I'm sure everybody is very tired. So let me first assure you that you don't have to take notes. I'll make these slides available to anyone who's interested. And also, because again people are tired, I won't dwell on anything technical, I think, and confine myself to very general comments. Now, any of the experts who find such general comments irritating, of course, are very welcome to object along the way. That's perfectly fine. So I guess over the last many years, I've spent some time. This is the first generality, dwelling on this diagram a little bit, where you have Diophantine geometry, the study of maps between schemes, roughly speaking, and applications from various theoretical frameworks to the problems that arise in Diophantine geometry. Now, if you look at the left-hand side first, which is probably better known, there's something very curious about it, for me anyways. I've never quite understood it, because on the one hand, of course, the motivic theory formalism is supposed to apply to Diophantine geometry in the general sense, in the sense that, for example, L functions are supposed to give access to Diophantine invariants, or invariants of a Diophantine nature, let's say. But it's very hard to make that direct in most situations. So in order to make that statement slightly more precise, let me move on to another generality. Suppose you write down some definition of points of a motive, something like this. Now, I put it in question marks because I don't know how often this kind of assertion would be reasonable. It seems to, there are a number of situations where there might be a conjecture of this sort. And maybe somebody has some different idea of how you might define points of a motive in a more general situation. But anyways, the point is that a definition like that, or anything similar, I think, would not really normally give you access to points of a scheme. Unless the motive in question is H1 of an abelian rarity. That's the one situation where you expect to actually get at the point. It's intentional in some sense in the case of motives, because deliberately the category of motives has enlarged the number of morphisms most of the time, so it wouldn't make much sense to be able to recover scheme theoretic points in the sense of Diophantine geometry. Even then, we often complain that there aren't enough morphisms, but anyways, there are more morphisms than schemes. So this is somehow built in. This difficulty of getting direct access to Diophantine information is built into the theory of motives. This doesn't mean that one can't apply it in different ways, because as we know, say two of the most celebrated Diophantine theorems of our times does apply motivic machinery in some sense. But that way, you actually, well, basically the idea is you use points of a variety to parametrize motives. And that family that you parametrize has the properties necessary to prove finiteness or non-existence in certain situations. That's the way the applications to actual Diophantine problems have been carried out. But always it requires a great deal of ingenuity to construct those families so that you can apply it. And it's certainly not part of the general theory. Now, when you're doing non-abelian geometry, so for example, for a curve of higher genus, and in my discussion, I'll always fix a point, assume that we have a rational point, because that makes a number of the concepts, I think, much more clear than the general situation. So let's say we have a curve of genus at least 2 defined over Q with a fixed rational point. The previous X group in non-abelian geometry gets replaced by a non-abelian cohomology space of this sort, H1 with coefficients in the non-abelian état fundamental group of X bar, where G is the Galois group. So this is continuous non-abelian cohomology, and this H1 is of course a classifying space for torsors for this fundamental group as sheaves on spec Q. Now, this object is much more difficult in some sense than even that difficult extension in the category of mixed motives, but nevertheless, it has some potential to directly apply to the study of points. So for example, it's equipped with a very natural non-abelian Albanese map that associates to points on the curve the torsor of paths from your fixed base points to that other point that might be varying. As x varies, so one studies these torsors. And the advantage of this over the motivic formalism is that this map does not extend to cycles. It's built up in such a way that it doesn't abelianize in any obvious way. So maybe one can do something with it when you're really interested in scheme theoretic points. And from the point of this view of this map, this H1 should be viewed as a kind of non-abelian Jacobian, therefore. An étale version of the non-abelian Jacobian. And there are some very nice things about this construction, even though that H1 is very difficult. In particular, other people, of course, study other kinds of non-abelian Jacobians. Maybe the best known is the moduli space of vector bundles, for example, which was proposed, as far as I know, in this famous paper by Weil, Generalisation des fonctions abeliennes, which gave rise to tremendous amount of mathematics. But people who read the introduction to that paper seem to be aware now that Weil's real motivation, maybe not, well, certainly one of the main motivations in that paper was the Mordell conjecture. He seems to have been quite interested in seeing if some non-abelian version of the Jacobian could be applied to study real points on curves of higher genus, the problem he detected in his thesis. Now, it doesn't quite work out. Oh, by the way, so why does he do these things like moduli space of vector bundles? In the introduction, he points out that he feels like non-abelian pi1 should be somehow relevant to these kind of questions. But in those days, there wasn't an arithmetic theory of pi1 of any satisfactory nature. So by making the representation space of pi1, suitable representations, into a completely algebraic space, like the moduli space of vector bundles, you could get models of pi1 in some sense that are defined over the same field as the curve. This seems to be, as far as I've read the paper anyways, one of his motivations for constructing this kind of correspondence, which later became much more complicated in non-abelian Hodge theory. But anyways, you can't really do much with it. I think, well, there might be many reasons. I really don't know, haven't thought about it very deeply, but people haven't applied that kind of moduli space to Diophantine problems as far as I know, not in any direct way. And there might be other reasons as well, but I think about it very naively. And one point of view is that if you construct moduli space of vector bundles, there's no natural Albanese map that will take points to a bundle or something like that. That works for line bundles, but there's no way to really do it in any natural way for higher rank bundles. Whereas, of course, if you take this point of view, there's a completely natural Albanese map staring at you, which at least the concept of it is very, very simple. Nothing fancy is required there. Right. Now, regarding that non-abelian Albanese map just introduced in this profinite setting, there's Grothendieck's section conjecture, which is, in this form, can be stated as the fact that that Albanese map is a bijection. This is equivalent to the different forms that you've seen. If you've never done this before, it's a good exercise to work out that it's equivalent in this setting. Now, I'll make a few remarks about this conjecture. First of all, as many people have pointed out, the injectivity is already known as a consequence of the Mordell-Weil theorem. Even if you replace pi1 by its abelian quotient, it's still injective because of the fact that other than the origin, no other point will lift rationally to this abelian tower. There is no point is infinitely divisible. Now, but the difficulty, as we've all agreed, is surjectivity. It's to prove that every pi1 torsor is actually the torsor of path coming from a point. That's what the assertion is. Right. It's instructive, in fact, to compare it with another conjecture, this time just for elliptic curves. If you take the points of an elliptic curve and take the profinite completion, it should be isomorphic also to something of a similar sort involving the fundamental group. The only difference is that you need some local conditions here. That's what the subscript F stands for. These are local conditions. People call them somewhere conditions. But once you put in the local condition, you're supposed to have this kind of bijection even for an elliptic curve. Right? And it's a consequence, of course, of the finiteness of the Tate-Shafarevich group. You get something like this. So the comparison between the two situations is a good thing to make for several reasons. For one thing, my feeling is that the techniques that go into this kind of assertion at least should inspire some of the way we think about the section conjecture in general. That's one reason. The second reason is for people who've never thought about non-abelian things, this comparison probably makes clear the difficulty of the problem. Because as we know, even for elliptic curves as well, maybe I'm not prepared to say one is more difficult than the other, but we're all aware of how difficult this kind of question is when we apply it to elliptic curves. So you shouldn't expect that one a priori to be any simpler. So that's where things lie in some sense as far as this comparison is concerned. One more comment is that if you think about the comparison with this assertion in the abelian situation, it should lead you to feel like there should be some Diophantine applications of the section conjecture, which is the way this conjecture works, of course. If you want to do explicit descent on elliptic curves, of course, you're assuming something like this. So this is strongly suggestive of well, other than the fact that this bijection is by itself interesting, maybe, but it's strongly suggestive of rather deep Diophantine content of bijectivity of that sort. And finally, regarding the conjecture, for me, anyways, when I first heard it in the late 80s, what it seemed to say is that the set of rational points, even on a curve of higher genus, has a certain categorical structure that's completely intrinsic to the fundamental group, meaning it's the set of isomorphism classes of torsors for pi 1. And this should tell us something about the structure of rational points. I'm not speculating what it should tell us, but this seemed to be somehow an interesting assertion out of which that we should dwell on somewhat. So that's another aspect of the section conjecture. Now, as I said, today I'm going to talk mostly about this Diophantine content of assertions of this nature, but it's quite difficult to do it with the profinite fundamental group. It's a very difficult object to study, as everybody knows. And so we're going to do this in a modified setting, which somehow makes these two arrows in the beginning diagram complementary. Even though they've gone in somewhat different direction, the way I've discussed it even just now, they are kind of complementary. In order to do that, first of all, let's remark briefly that this kind of formalism can be set up in any theory of pi 1, where you have base points. Now, the important thing is, of course, to have theory of pi 1 or theory of paths, homotopy classes of paths, with varying base points. And whenever you have this kind of situation, you can try to study points. Because in any such setting, the space of paths will be a torsor for the fundamental group, and you'll vary inside some space, some classifying space for torsors, and maybe the geometry of that space can be accessed in some situation and give us insight into points. So one might speculate about something like this, especially since we do have many theories of pi 1, where it comes with natural structure associated with the arithmetic geometry of the scheme. Right. Oh, by the way, so in regard to what I said earlier concerning the application of the theory of motifs, so here as well, we're proposing to study a variation of some sort, but here, contrary to, say, faulting theorem or the theorem of Wiles, the variation we're proposing to study is completely natural or intrinsic to the curve. It doesn't require any ingenuity to study this variation, so that's something of an advantage here. Right. Oh, wait, one other remark was that I said this thing about not having an arithmetic theory of fundamental groups at the time of A, and that's not completely true because, of course, even then people had some idea that a kind of Galois group should be a fundamental group. But as far as I understand, the thing that was really missing was a theory of base points. The idea that a Galois group should be interpretable as a fundamental group is a very old one, I think. I guess it's even in Hilbert's ideas about class field theory in some sense. But the idea that you can vary small base points, I don't think you can build it into this large Galois theory in any natural way, as you can in Grothendieck's theory. So that's a big deal somehow, which even after the definition of Grothendieck's fundamental group, I don't know whether people really applied it, because there are so many constructions you can do that don't depend on the base point. So now when you want to use something that depends on a base point, it's hard to sort of imagine using it in a creative way, except, of course, I learned this kind of thing from Hodge theorists like Hayne, who really emphasized in Hodge theory the importance of the base point. Right. Okay, now, So returning to the study of the Albanese map, the setting in which we're going to use it is this unipotent setting of the motivic fundamental group that was discussed by Professor Dlin in the 80s. Now, this ends up being a system of realizations. I don't understand any other formalism myself. It's a system of realizations corresponding to the cohomology theories that I'll say something more concrete about in a few seconds. But I should remark that it does lie somewhat between the profinite fundamental group and homology, maybe in a precise sense as well, but certainly in complexity. The profinite pi 1 is very, very hard. Homology, maybe we feel like we have some understanding of at this point. The motivic fundamental group is in between, except it's much closer to the bottom problem. It's much closer to homology than profinite pi 1, and it's much easier for that reason. But it's non-abelian, which makes it carry somewhat more content than what you get just from homology. For example, we had this X group in the case of motives, but we can again, in this setting, study non-abelian cohomology with coefficients in the motivic fundamental group. And as I said, it's more tractable than the profinite version, but still it carries more information than the homology. Of course, as I said, we'll only be discussing these fundamental groups at the level of realization. So this is also just going to be a collection of classifying spaces with certain compatibility properties corresponding to the realizations. So the most important part, in fact, is this QP et al. Realization that was already referred to in Decane's talk. I guess it was your talk, right? I don't remember. Yeah, you discussed unipotent completions in general, and this is the QP unipotent completion of the profinite fundamental group, which comes in a tower corresponding to the descending central series, right? So that you can set up a tower of Albanese map of this sort, which are all compatible. So now, in this next portion is the part that everybody hates about these slide presentations. I'm going to go through a whole bunch of slides very quickly. But you're invited to not pay any attention and take this diagram as kind of a black box. But just for my own comfort, I do have to discuss the construction just a little bit. So bear with me as we go through a bunch of slides quickly. Right. So I'll explain what's going on, this picture, just in very brief terms. Right. The unipotent fundamental group itself, you can give it one of these Tanakian definitions that on the et al. Side of X bar, you have the category of locally constant unipotent QP sheaves, right, where unipotent refers to the fact that it can be obtained by a successive extension of trivial sheaves, constant sheaves. On that category, you have the fiber functor defined by any point that associates to a sheaf its talk, and the unipotent fundamental group is defined to be the tensor-compatible automorphisms of that fiber functor, which of course you can do in a very functorial way, making it into a group scheme and so on. But anyways, it's a pro-algebraic, pro-unipotent group over QP. It's equipped with this descending central series whose quotients are ordinary unipotent algebraic groups. And at the very bottom, it's just homology with QP coefficients. So that this H1, which is a non-abelian as you go up the tower, at the bottom is just the usual H1 with coefficients in the Tate module of the Jacobian tensor QP. But this descending central series, of course, is one of the things that enables us to study this H1 as opposed to the whole profinite thing all at once. So at the very bottom level, so as I said, it's just U1, but then they're all connected together by these exact sequences so that we can somehow take apart this structure level by level. And this is the convenient thing about this unipotent situation. The unipotent group has a natural action of the Galois group because of the functoriality of everything that's going on and the fact that we chose a rational base point. And it lifts the usual action on Tate module that has been studied a great deal. So it's a non-abelian action, which we're trying to use in some way. And with respect to that action, we can define non-abelian continuous Galois cohomology with values in the points of UN. But as I said, it doesn't have a structure of a group. It's just a pointed set, which is a good thing, as I've already said, as far as studying points is concerned. And I will elaborate on this further later. There's this whole cohomology, but remember there was a subscript F in the tower corresponding to a large collection of local Selmer conditions. you require the torsors that are classified here to satisfy a bunch of local conditions. For one thing, you say that you require it to be unramified outside the set of primes of bad reduction and P. Yeah. And there's a crystalline condition at P coming from periodic Hodge theory, which requires a torsor to be trivialized when you tensor with B cris. So that's the condition. So it has to have a B cris point. So as I said, if you don't understand that, that's okay. You can ignore that and I can explain more later. But when you've put in those conditions, the good thing is that these things become much smaller than the whole Galois cohomology. And in fact, this whole system becomes a pro-algebraic variety over QP. You can put it on in naturally the structure of a pro-algebraic variety. Each level becomes a QP algebraic variety that I'm referring to as the Selmer variety now of X. It's like the Selmer group, or QP version of the Selmer group with the local condition, except it's not a group, it's a variety. And in fact, each of the transition maps are also maps of varieties, so that the whole thing you can think of as a moduli space of principal bundles for you on the tau topology of now spec Z with S inverted that satisfies furthermore this crystalline condition at P. But in order to analyze this crystalline condition, of course, is a little bit difficult. So it's convenient to realize this naturally as a subspace of just this restricted ramification cohomology of the Galois group of the maximal extension of Q unramified outside T, right, with coefficients in UN. This one is already a finite dimensional variety, that is, and H1 sub F is defined as a subvariety in a suitable way by further imposing this crystalline condition. Now this thing, so I'll just make a brief remark about how this last object acquires a structure of a variety. But the way you do it is using that exact sequence that takes apart UN in levels. So the idea is that there is a long exact sequence of non-abelian cohomology associated to this situation. Okay. So you put the variety structure on it level by level. So if you've already put it onto the n-1th level, n-1st level, then you have this boundary map that goes to H2. Now H2 will always just be a vector group. That's always an abelian thing, just a vector space. So you have a vector group structure on there, and then you prove that that map delta is an algebraic map. So that its kernel is a natural subvariety of that H1 at the n-1th level. And then the thing in the middle can be realized as a torsor for that other vector group over the kernel of delta. That's the basic construction. There are a few technicalities involved in doing these things in a functorial way enough to say that everything is algebraic, and that the algebraic structure is canonical and that the maps are algebraic and so on. But that's all fairly easy. It's just mildly technical thing, and the idea is what I just said. But as I said, wrote here, the boundary map, however, is a nonlinear map in general, and that's something you have to be careful of every now and then, and that already occurred in Duquesne's talk, the nonlinearity of this boundary map. So this is how you put the structure of a variety on these cohomology, and as I said, H1 sub F, then this further crystalline condition is defined as an algebraic condition. You can do this locally as well to make everything algebraic, so it becomes a closed subvariety of this unramified, restricted ramification cohomology. I've already referred to the fact that the map from the points of X just goes by associating to a point the principal U bundle of paths, unipotent paths from B to X. So that's exactly as in the profinite case, where you can define it to be the tensor compatible isomorphisms from the fiber functor at one point to the fiber functor at the other. For n equals 1, this just becomes the usual map from Kummer theory. You use the base point to embed the curve into its Jacobian, and the Kummer theory and the Jacobian will give you a map of this sort. Right? So then this is nothing new. So our tower is actually refining this map from Kummer theory, except the map from Kummer theory maybe one could also try to use to study points, except because of the fact it factors through the Jacobian, you can't sort of dissociate the points, sort out the points of the curve away from the points of the Jacobian. This is an old story, old problem in studying points on curves. So that maybe what we're hoping is that using the tower, the Jacobian just doesn't get in the way at all right from the beginning, right, just from the formalism. Now, there are also local analogs for which I won't give a separate discussion. You just restrict the Galois action to the local Galois group at P, and then everything else goes through in exactly the same way, except now the map is defined on QP points as well. But now the important point is that this local map can be described. The global map is still very mysterious, but the local map has an explicit description in terms of periodic Hodge theory. This is the technical backbone of this whole construction. That by using a comparison between the tau fundamental group and a Duram fundamental group classifying unipotent vector bundles with flat connection, what you can do, together with the sources, you compare all of those guys in such a way that you actually have an isomorphism between this classifying space for crystalline torsors for UN and a classifying space for torsors for the Duram fundamental group. Except for that, again, because of this fairly linear nature of the Duram side, it has a very explicit description as a homogeneous space for the Duram fundamental group, where you just quotient out by zeroth level of a Hodge filtration that comes from this Hodge theory of the fundamental group. So there's a very explicit description for the Duram classifying space, which makes it possible to actually study this map. There's a crystalline structure, as I wrote there, that I'm suppressing. There's a Frobenius action on the Duram fundamental group, as well as the torsor space that comes from comparison with the crystalline fundamental group. But anyway, so that's an essential part of this classifying space, but I won't discuss that too much. I'll just say a word about the map. What is this map from étale torsors to Duram torsors? It just takes an étale torsor, which comes with a coordinate ring that has a Galois action, and applies Fontaine's functor to the coordinate ring. So you tensor with B-Chris and take the Galois invariance. Then that gives you another algebra whose spec is exactly a torsor for the Duram fundamental group and gives us our map D. Yeah. The idea that the fact that this is a compatible construction is contained inside the commutativity of the diagram, which is actually just this assertion, non-abelian periodic Hodge theory assertion, that these two fundamental groups as well as torsors are isomorphic once you, together with all the structures, once you tensor with B-Chris. Yes, I didn't write down the proper attributions. This, for example, is due to a number of people like Vologotsky had a proof in certain situations, Faltings and Martin Olson wrote down the most general version, I think. But most of the other things are, I guess, I should have put more attributions, but this one is especially difficult assertion, so I'll mention those names. The other attributions, I guess, are so well known that I don't have to write it down, like Professor Deline's construction of the motivic fundamental group and so on. Yeah. Right, now, actually, so I said that this local map is easy to understand. So the point is this map to the Duram space is the thing that can be somehow explicitly computed. And the way you compute it is using periodic iterated integrals. So you write down a universal connection depending on choice of a basis of differential forms. And having done that, you can actually explicitly describe the coordinates of this map with respect to a basis using periodic iterated integrals. I won't bother you with any precise formulas. But this fact is very important because it indicates that the map from points to this Duram fundamental group, that's an algebraic variety, of course, as well, or pro-algebraic variety. But the coordinates of this map are all highly transcendental functions. In particular, the map has Zariski dense image. Not the map, not just the whole map, but any residue disk of any point will in fact have a Zariski dense image, and that's very important for applications of this construction. And this is because well, okay, yes. So it has a Zariski dense image, and also what I wrote on the last line. It can be expressed, therefore, on every residue disk. The functions you obtain can be expressed as convergent non-zero power series. Finally, as far as this general construction is concerned, the local and global maps fit into this compatible sequence of diagrams, one for each n. So you can look at the global points, local points, Duram, and the tau realizations. But one widely philosophical way of looking at it is that the inclusion of the global points inside the local points is very mysterious. It's hard to really understand how it sits in there. But the maps at the bottom are all just maps of algebraic varieties, so maybe we can do something with it. And this idea, so in this form, this comment, it goes back, as far as the inspiration is concerned, to this idea of Serge Lang from long ago, where he thought that could take any finitely generated subgroup of the Jacobian and maybe prove that it intersects the complex points of the curve in finitely many points. So that was an old idea which people never managed to actually carry it out until the non-abelian conjecture was proved, and then you could derive it as a consequence, but you can't use it for proof of finiteness. But here, something like that does, it becomes more possible as you go up n by replacing the Jacobian entirely by this big global summer variety classifying space and using p-adic points instead of complex points. And the points of the the analytic points of the Jacobian will be replaced by that local classifying space. So then something, it seems, can be done, at least in certain situations. Right. So in fact, let me explain to you one very general theorem on what can be done. Oh, so I introduced a bit of notation without explaining. This composed map that goes from the global classifying space through the localization via this p-adic Hodge theory map, Fontaine's map, I'll call just the log map at P. That D is sometimes called the log map in the Bloch-Kato theory for abelian coefficients. So it's the Bloch-Kato log, so I'm just calling it the log. So here's the theorem. Suppose for any given n, you can prove that the image of the global classifying space inside this drum classifying space is not Zariski dense. Then automatically X can have only finitely many points. So that's a basic finiteness theorem, which requires no effort. It just follows from the formalism so far. Mm-hmm. That's right. It's a map of algebraic varieties. That's right. It is a question about it. That's right. Whenever one can actually prove something about this, you prove something about the dimensions. That's right. Yeah. And the algebraic structure is very important for that kind of argument. That's why I made this comment earlier that somehow you're replacing the inclusion of global points by the map of algebraic varieties. That's right. Yeah. So roughly speaking, that's right. There has to be some transversality between these two images. That's right. So I'll explain that in a second. Yeah. So in fact, yeah, that's what comes out in the proof. So this is the whole proof, actually, this diagram. You don't need much more.
So since you want to this is Chaboti's idea.
That's right. Yeah, you're right. Yeah, okay, yeah, I should have said that. That's right. This is Chaboti's idea, by the way, which is also referred to in this section of Lang's book where he makes this conjecture. He had Chaboti in mind when he was discussing this finite degenerated subgroups of Jacobi. That's right. So for n equals 1, this is essentially the method of Chaboti. That's what it is, except it's a cohomological version of it. Right. So here's the proof of the finiteness. So we're assuming that the image of the log map is non-dense. So there's going to be a function on this the homogeneous space that vanishes on its image, some algebraic function phi. So you pull it back to the local points of the curve, and then it has to vanish on the global points by the commutativity of the diagram. But we just said a moment ago that any such non-zero function pulled back to X will give you a non-zero convergent power series on every residue disk. And such a thing can have only finitely many zeros. So that's it. So that's the finiteness, assuming non-denseness of the image of that log map. All right. So as I said, this hypothesis is something that should give us pause, of course, but nevertheless, it indicates the formalism is somehow may be useful for studying points. So what can we do? Well, I'll say in a second, but first let me make the general remark. It's probably reasonable to conjecture that the hypothesis of the theorem is just always true. Yeah. For example, it would follow from an assertion of this sort that seems to be very widely believed, that if you take suitable extensions of the trivial motive by a positive weight motive, then they should all be trivial. Yeah? So for example, if you believe one of these reducible versions of the Fontaine-Mazer conjecture, that is H1 sub f with coefficients in the motivic representation should also all be motivic, then the existence of a weight filtration will imply this kind of assertion. So motivic nature of enough extensions give you such vanishing. Also things like the portions of the Bloch-Kato conjecture where they say certain Chern class maps should be surjective. And then by just saying that certain parts of K theory just doesn't exist, it's just zero, you get this kind of vanishing. So this is consistent with a large variety of conjectures in the theory of mixed motives. And it's somewhat interesting because I already pointed out that the section conjecture is a non-abelian version of the finiteness of Shah. And Grundig thought that they should, had this idea that they should be related to the finiteness of points, yeah, which we still don't know how to make that work. But all these other assertions, like Fontaine-Mazer conjecture and so on, you can view them also as being somehow a higher non-abelian finiteness of Schwa. Well, I don't know if everybody would agree with this view, but in any case, that's what comes into the finiteness of the points in this approach. So it's slightly amusing. Maybe there's something in there worth thinking about. The other comment in relation to the station conjecture is that if you look at this local map from the points to the local classifying space, I pointed out that this has a risky dense image. It can't possibly be surjective, of course, here, because the dimensions of these things will grow quite quickly, but it does have dense image, so it's about as surjective as it can get, and that's also a part of the finiteness. So it's somehow close to using a local section conjecture of some sort for the proof of finiteness. So these two facts, for me anyways, are still rather interesting. That there's always this surjectivity type of statements that seem to go into the finiteness. Now, what can be proved as far as this? So what can we do about actually using this theorem for actual finiteness? Is this is the there are other scattered cases that one can handle, but here's the only systematic assertions that I can make. So you can set up affine analogs with integral points rather than rational points. I didn't discuss that for simplicity. And then one can often do something like for P1 minus 3 points, okay, or an elliptic curve minus a point. You can prove finiteness of integral points in this setting, provided, well, in the elliptic curve case, it has complex multiplication. Right? And then for compact homogeneous curves whose Jacobians have potential complex multiplication. This is a full list of sort of systematic settings where one can prove the hypothesis of the theorem and thereby get actual finiteness. So in other words, we can do this in situation where the image of the Galois group acting on homology is essentially abelian. So somehow it's very hard to move beyond this at this point. To control the way the Selmer variety behaves, we can do it in these settings, yeah, but not in any seriously non-abelian situation. That's the difficulty. But anyway, so for example, you can prove finiteness of points on the Fermat curve using this method.
This only for rational points or for over any number?
For these assertions, just for rational points. Yeah, so although this general fact will hold for any number field if you choose to just modify it suitably, but when to expect this to hold, I don't know at the moment. Yeah. And in fact, these implications also just work for rational points. Maybe that's another place where somehow the whole story is similar to the Birch-Swinton-Dyer conjecture in some ways, because over Q there are many things one can do, but things change quite dramatically with the field, which doesn't happen when you're doing Diophantine geometry using heights, for example. There somehow it doesn't care so much whether you're over a number field or Q, but here it seems to be quite sensitive. Right. So maybe I'll outline this, how one proves this last thing, just to give a flavor of the arguments. I won't give much detail, but just say something about this. And the idea is that U is still, this unipotent fundamental group is still very complicated, so one constructs a quotient by going modulo the second level of the derived series. And then one gets a group that has much simpler Galois theoretic structure. Yeah? So that you can just extend the diagram to put something involving just this quotient at the bottom. Yeah? And when you go down here, so what we can prove is that at the bottom level, exactly what Matt said earlier, is that in fact the dimension of this global classifying space is eventually just less than the dimension of the local classifying space. That's what one can prove. So once that's true, of course, this map will have non-dense image. This map is surjective, then that map also has non-dense image. In any case, it's better to work just with the bottom groups in any case in this setting. So working with this quotient is the way one proves these things. Now, what does one do with those quotients? So again, let me give you an idea of how we prove this theorem that on bounding the dimension. So most of it is quite elementary. So first of all, this cohomology with this F subscript, crystalline subscript, remember it was a subspace of the restricted ramification cohomology, so we just have to bound the dimension of the larger things if we want to control things. And dimension of that restricted ramification cohomology can be built up out of these completely abelian pieces by summing up over the associated graded quotients, so you have the second inequality using the long exact sequences. So eventually, you can just study, to control the dimension of those spaces, you can just study these abelian usual vector representations. And there, a number of things happen. For one thing, there's an Euler characteristic formula for any such representations that I've written up here. Now, however, for these representations, the H0 term always vanishes. Right? And so you can express the H1 in terms of this minus part, where the complex conjugation acts as minus, and an H2. So you get a formula of this sort because of the vanishing of H0. Now, here's what happens. That minus part can be easily controlled. This fundamental groups actually have a fairly explicit structure by relating it to the topological fundamental group, so that you can count all bases for free Lie algebras, essentially, and then some suitable quotients of that in such a way as to get a very quick, easy bound for that minus part. So that looks like this. So it grows like n to the 2g over 2g factorial with that coefficient 2g minus 1 over 2, and the rest is of the lower order. So that's an easy count. Sorry?
Are you really using the minus part?
Yeah, the dividing by 2 is where the minus plays the role. That's right, yeah. Now, then one has to do something about that H2. That's the main difficulty. Which is, now, but before I get to that, let me point out that on the drum side, on the other hand, the dimension of the drum classifying space, that can also be counted in a very elementary way using Hall basis, giving a lower bound, where you have n to the 2g over 2g factorial now with a bigger coefficient for g at least 2. So it becomes for 2g minus 2, so that's bigger than 2g minus 1 over 2, as long as g is at least 2. So this is a lower bound for the dimension of the drum classifying space. So eventually, the dimension of this minus part will grow more slowly, will be less than the dimension of the drum fundamental group. So it suffices to show that that H2 is not so big. So that's the idea. Now, the H2, by the way, is when you put in the subscript, this H2 is the thing that should be 0, actually, eventually, according to the conjectures. But one can't prove that. Seems to be very difficult. It's related to a lot of vanishing conjectures on Galois cohomology, but all of which seem to be difficult. But this kind of bound we can prove by very general, actually elementary arguments. So this controlling H2, of course, is the kind of thing where Iwasawa theory typically comes in, and this is where we use commutative Iwasawa theory. So I won't say much about, there's a bunch of standard stuff in the middle that I won't bore you with. I'll skip directly to the Iwasawa theoretic statement that's involved, which is this. Eventually, you have to study the Hums from a given Iwasawa module to these representations, dual of these representations that occur here. By Potter-Tate duality and controlling some local things that are easy, you reduce to the study of these gamma invariant Hums from an Iwasawa module, where gamma here is the Galois group of the field obtained by the p-power torsion of the Jacobian, where at the bottom we start with some small field that where all the Cm is defined and that contains the p-torsion of the Jacobian. So you have to control that Hum, and that M there is the p-Hilbert class, Galois group of the p-Hilbert class field of this big non-abelian extension in general, but here it's abelian, of course, yes, right? So this one is abelian. So that's the important part. So one needs to control that Hum.
Expressed numerically to get the unramified extension of that infinity.
Oh, that's right. So yeah. That's right. So in this asymptotic argument, somehow the local stuff counts for nothing. So for this reason, as John is pointing out, you eventually just have to control the Hums from this unramified extension, the Galois group of the ideal class group. You don't have to control any p ramification when you go up the tower somehow. Whereas in the theory of elliptic curves, you'd always have to struggle with the p as well. So this is something of an important difference. And it's important here because, in fact, as John points out, this M is torsion in an easy way. So this is torsion. I guess here there was attribution necessary as well. This is due to Greenberg, is that right? This ideal class group is torsion over the Iwasawa algebra. And it's finally generated as well, and we really don't need anything more than that. That's what's interesting maybe or hopeful about this argument. So we need to, in other words, there's an annihilator for that guy, the sum power series, which annihilates the Iwasawa module in question, so to have a non-trivial Hom, it has to annihilate the characters that appear. It has to vanish on the characters that appear inside each of these representations to get a non-trivial Hom. But you can just write down those characters. If psi I are the characters that appear inside H1, the ones that appear inside these quotients, these are spanned by I tuple brackets of elements from H1. So you can just write it down explicitly in this form. Yeah, and count them. So these are these span the integer points in some simplex, okay, right? And you count the possible Homs from the Iwasawa module. In other words, the possible zeros among these characters of this annihilator, which is, well, of course, morally should be a p-adic L function of some sort, although not in the usual sense. Now, there's a lemma of Greenberg that allows us to, this is just a mild technicality, but reduce to a power series of this form where it's a polynomial in the last variable. And then you see that if you count the zeros of this thing inside some simplex, the last variable only counts up to some finite height. Yeah? So that, in fact, you're only counting in a simplex of one lower dimension, and there are only n to the 2g minus 1 of those guys. So that's the whole counting argument. So this Hom is eventually bounded by this O of n to the 2g minus n that we wanted. So that doesn't count for much. So asymptotically, we get this bound, yeah, for sufficiently larger. And that's all there is in proof of finiteness for curves with CM Jacobians. So my feeling is still this is much easier than most other proofs of finiteness that I know of. And so should provide some eventual advantage in studying these questions in some explicit way.
Do you have some quantitative Iwasawa module graph function? Can
You do know that kind of torsion, locally torsion statements for relevant Iwasawa module in even non-abelian situations, but you don't know. You still can't control these Homs somehow in a reasonable way. At least I don't know how to do it. I was hoping that the experts in Iwasawa non-commutative theory would be able to help me, but that's a very good question because, of course, in fact, that was the second line I wanted to make. Contained inside this proof is an obvious suggestion for the non-abelian statement, kind of statements that one would want to make it work for general class. You're exactly right. So one does know something anyways. One knows that the corresponding Iwasawa module, in fact, is torsion. That was Otmar's theorem in his thesis, I think. And so one needs to control those Homs, but I don't quite know how to do it as yet. Nevertheless, as I remarked earlier, it's interesting that the finiteness of points still in this case is in some sense accounted for by sparseness of zeros of something that should be an L function, which stresses furthermore the analogy with the theory of elliptic curves. It's not quite the same, but there is some counting argument for zeros that eventually inputs into the finiteness. That's quite interesting for me. Sorry?
No, I mean, probably that module is always pseudo null. We can't prove it.
Right.
So the L function is probably 1.
Uh-huh.
But of course, you want an annihilator.
That's right, yeah. Now, there's some, nevertheless, the proof is very unsatisfactory. In some sense, it's kind of, this dimension counting is just an argument maybe that indicates that these structures are interesting, and one should be able to do other things with it. Among them, a reasonable short-term goal, you see, is when I gave you this conditional proof of finiteness, one should be able somehow to exhibit this function that vanishes on the global point. Yeah? In other words, if you can actually construct a function that vanishes on the image of this global summer variety, then by pulling it back to x, you get a power series that vanishes on the global points, which in principle, maybe you can use to find points or bound points. So eventually, this should, the hope is that this will lead to more effective methods for dealing with points. So this seems to be the most serious immediate problem with this method. How does one construct such phi? Now, so I wrote down some other general vague comments that you should give a cohomological construction. So the discussion I gave so far in some sense was purely on the drum fundamental group side, but what you really want is a cohomological construction because that's the thing that would relate directly to a global object, namely the global summer variety. Yeah? So this is a problem which I'm beginning to have some ideas of how to address, although it's still very difficult. Oh, by the way, this is the way finiteness is again proved for elliptic curves in a number of situations. Like the method started by Kolivagin, and I guess it's most complete in Kato in the L non-vanishing case to prove finiteness. It's exactly, in some sense, it's producing this cohomological function that vanishes on the image of the global cohomology. So this is, there should be something similar going on here in a way whose full formulation I don't quite understand, but at least there is an example I can give which shows you the kind of things one should expect. As I said, so there's this general argument about dimension where counting of zeros is involved. This isn't something like that. This is something more explicit, which isn't directly related to L functions in any way. But anyways, maybe hope gives some indication of what one should be trying to do. Here, the example is affine, not in the compact higher genus case. So take an elliptic curve minus a point, where now we assume that the elliptic curve has rank 1 and finite p part. Sorry, did I say 0? No, it's finite is enough. Yeah, sorry, finite p part. So I'm told that this is the kind of thing one can actually check. I don't know how to check it, but people can check it. So, and the consequence is that for one thing, the global points inject to the H1 part of the P local cohomology. So, sorry, it's a bijection. So that's one convenient consequence of our assumptions. And H2 will be 0 with coefficients in the Tate module. So these are critical to the subsequent discussion. So this is what I use those assumptions for. So this is a very special situation. But nevertheless, even in this setting, of course, finding integral points is not trivial, even if you know that the whole thing is just rank 1. So how do you sort out where the integral points lie inside the Mordell-Weil lattice? So what can one do in the direction of what I indicated a moment ago is this. Here, we can construct a diagram of this sort involving the integral points. And this psi here will be given constructed in a cohomological fashion that annihilates the global points, except I have to replace by a slightly more refined Selmer variety. I put a subscript z there to indicate integrality, where we're now looking only at classes that vanish at all places other than P. You can prove that the integral points of the curve all give rise to such classes. So it's all concentrated at P. So we set up this diagram. So how does one construct that psi? So I'm just going to give a very brief description. As I said, I didn't want to tire people out late on Friday afternoon. So here's the description. So first of all, let's give a quick summary of how that H1 space, how this cohomology space is defined from the beginning. So if you look at the Lie algebra of the second unipotent level, oh, sorry about that, I forgot to mention. Here we're just going to use U sub 2. This is the first non-abelian part, non-abelian quotient of the unipotent fundamental group, and no more. Because of the rank 1 assumption, it suffices to work at this level. As a scheme, it's isomorphic to its Lie algebra, and its Lie algebra actually decomposes here. If we take a tangential base point, the Galois action is actually just split to between the Tate module and the kernel, which in this case is just QP1. So it's a one-dimensional central extension which actually split. Then the co-cycle condition for a co-cycle with values in U2, which we're identifying with L2, can be expressed just using the first simple part of the Campbell-Hausdorff formula as follows. If you write it in terms of the two components, you get d of the v component is 0, so that is a usual co-cycle. The second part is not a co-cycle in the usual abelian sense. Instead, it has a relation with psi1 written up above, right? Where that bracket refers to cup product together with the bracket that Romiar referred to, I think, already in his talk, or maybe Kirsten did. So this is the condition for a map to be a co-cycle in non-abelian cohomology. So this is why for conventional number theory it's somewhat hard to study, because you have to deal with all these cochains that aren't co-cycles, and we don't like to do that. Similar to how in differential geometry you don't like non-closed forms until you do non-abelian principal bundles and so on. So this is the same setting in a rather precise sense. Now, so here's the function. So I'll just write down the full formula. The function on a cocycle psi takes this form. First of all, so as I explain the second part first, you can take the log of the ZP cyclotomic character, or the QP cyclotomic character, which therefore can be viewed as a class in H1. It's just a homomorphism to QP with trivial coefficients. And then there was that second component, psi 2, right? Take minus 2 times that. That minus 2 has to do with the fact that the previous formula had a minus 1/2. And take the cup product, which will then lie inside H2 with QP1 coefficients, that is canonically QP. Now the first portion is slightly more tricky to explain. What you do is you take the psi 1 portion, and then you take the cup product with the log of the cyclotomic character. Then you solve this equation, dx equals that thing. And in fact, the point is that this has a global solution. Everything inside, the psi 1, because of this rank 1 assumption, as well as the cyclotomic character, of course, actually extends to functions on the whole global Galois group. And you solve this equation for a global cochain x. And having done that, you write down that cup product up there. And that's psi of psi. And its class is independent of the choice of x. So that's important in this discussion. So you eventually really get a map of this sort from this cohomology space to QP. And the theorem, which is very easy at this point. Oh, by the way, I guess I forgot to remark, this is actually a Massey product of some sort. It's a refined Massey product. It's a secondary cohomology product in this setting. The easy theorem at this point is that this function actually vanishes on the image of the global classes. And that's because of this, actually, the standard exact sequence for H2. You see, if you have a global class, you could have carried out the construction already at the global level. So your local H2 class actually comes from a global class. But that global class vanishes at every other place. We've set things up in such a way so it has to vanish at P as well. So that's the whole argument. So it vanishes. So you do really use this reciprocity in order to prove that this function annihilates global classes. So this, as I said, is a very special situation, but I think it's still very indicative of being able to do constructions of this sort in a much more general setting, which I hope to figure out eventually. But let me tell you something, give you an indication of the really explicit formulas one gets out of this situation. So in the previous setting, choose the Weierstrass equation, and then you get these differential forms. Right? Associated to that, we'll get functions given by Kalman integration, as above. So you integrate those forms from B to Z, and there's this unique path in this p-adic setting, Frobenius invariant path, and we're integrating along there. So there's no period in this case, which makes it substantially easier than the kind of things I should have also mentioned, as far as attributions are concerned. This map to H1 in the Hodge theoretic setting was constructed by Decane many years ago in, when was it, 1989 or so, I guess. Yeah. Except there, it's much harder to use somehow because there are periods for one thing, and the image is not an algebraic variety, it's a complex manifold. But here there are no periods, so somehow it seems to be an advantage of the p-adic setting. So anyways, you get these functions, analytic functions defined by integration and iterated integration. Right? So in terms of this function, if you interpret this theorem, so here's what happens. Suppose you had two integral points y and z on the curve, then you have this relation between them. So that's an explicit equation which follows from the previous annihilation theorem. Now, so how would one use this? Yes, if you already had one integral point in hand, say y was an integral point that you already have, then that log square of y term is not 0, so you can divide by the whole thing. And well, whichever way you do it, you can interpret the whole thing as a function of z. And then you have an equation for all other integral points if you have one in hand. Unfortunately, I don't have any formulation where you can avoid starting with one point. You do need to start with one point to get such an explicit formula. But nevertheless, if you're given that, you can find other points in principle by searching for the zeros of this explicit analytic function. And there is a very curious symmetry, of course, to this equation that makes you feel like one needs to understand it somewhat better. I'm afraid I really don't quite understand it at this point. But anyways, the formula is there. To prove it is also actually relatively easy. The point is that because of the splitting of the Galois action, there's a QP action on this whole cohomology space. And somehow, if you use that, what you do is you take the image of the point x and image of the point y inside here, and then you scale it so that they both have the same image in the abelian quotient. So then the difference between them will be something inside H1 with coefficients in this QP1, U2 mod U3, and that one can explicitly calculate without too much difficulty. So and so this QP star action is sort of immediately gives you these explicit formulas. So that's pretty much the end of any real mathematical content. Several people commented on the title of the lecture, which was very general and vague. So I guess I'll conclude then with some preliminary remarks, which are also also very vague. And as with a number of the previous comments, most everyone is invited not to take any of this seriously. So what do I mean by Galois theory and Diophantine geometry? Well, the point is that as far as I'm concerned, Galois theory, according to Galois, is about Diophantine geometry of dimension 0. You take polynomials in one variable, and the question is, what structure gives you the right insight on solutions of that equation? And there group theory comes in. So that is Galois theory in one variable. So already from the beginning, I think Galois theory is concerned with Diophantine problems. So then it's very natural to ask, if you have two variables, namely a curve, what is the Galois theory that addresses questions in analogous way, or maybe even in better way? And this is somehow, I think, a general question. There are other things people may call Galois theory in two variables already, but there seems to be, it feels to me like something, there should be a unified framework that puts together the machinery in such a way that makes it directly relevant to studying zero sets of two variable polynomials. As I said, nobody should take this seriously at this point. This is not to say that I don't take it seriously. I take it very seriously myself, of course. On the other hand, to make it really convincing to anybody else, of course, that's a task for a lecture at a future time. Thank you very much.
Questions, comments?
So when you look at this, the function with the dilogarithm type function you have here,
Right.
this one. So you describe it as an analytic function, but it's some locally analytic function on a finite number of patches, or what does it?
That's right. On every residue disk, it's the way these iterated integrals are constructed. Locally, it's just you just take antiderivatives. You would expand your differential form in an algebraic coordinate, say, and then you take that analytic function and just take an antiderivative. So then for the iterated integral, you do it again after multiplying by the other differential form. So it's a very explicit convergent power series once you have your form and local coordinate in hand.
So has anybody actually used it to try and find a point?
No, I'm not good at computation myself. So Kiran Kedwaya apparently knows how to compute these things, and he promised me that he'd do something at some point and see what happens.
In the section conjecture, you replace the Galois group with the pro-nilpotent completion. The application, the rest injective?
Injectivity, you mean injectivity? Sorry.
So points to H1.
Probably not.
Injective.
Injective?
Yeah, it all comes in the
But no, but this is QP coefficient, so I'm a little bit worried about torsion.
Maybe a vague question. Can you formulate in this setting the long conjecture for rational points on higher dimensional varieties?
No, maybe. Well, there are aspects of the formalism, of course, that work for any variety. Whether there's real relevance to finiteness at this point is quite difficult to say anything about, because any finiteness depends on the fact that things are in one variable. The local expressions are in one variable. So you need to find many functions to deal with higher dimensional varieties, and I have no idea how to do that at this point. But as I said, as far as Galois theory is concerned, let's deal with two variables first.
Perhaps I might just make the remark, Mignon, that even though it's infinitely worse than what you do, Siegel's old method for finding integer points for proving finiteness of integer points on curves, in theory, bounds every other point in terms of the height of one of them. This has never been sort of worked
Yeah.
out fully because the bounds are so horrendous. But in principle, it's doing, your formula, of course, is infinitely simpler and will do much. But in principle, the old method by Diophantine approximations does give that because the 2A Siegel method of proving finiteness of rational approximations bounds all rational approximations in terms of a good enough one.
Right. I see. Somehow this issue of needing one point seems to be consistent in the two settings.
Yeah, exactly.
I'm wondering whether you can understand this example with a point removed in terms of taking the pullback by the multiplication by p to the n, and hence getting a elliptic curve with many points removed, and then looking at the Chabot-T for the generalized Jacobian of that.
It could be. I don't know, but you probably
I was just
understand
thinking
that issue.
because you should be able to. That should be. You should be able to know what the rank of the integer points there are. You have just the elliptic curve part. That's rank 1. You have a torus.
Yeah, sort of. Yeah, it's possible. I don't really know, but if you do it that way, somehow it doesn't seem like these iterated integrals would come up.
Yeah,
Yeah.
it is. That's probably not.
So let's thank Mignon for his